Welcome to the second part of the Multiloop demonstration. Here we discuss systems, calculations, and exports. The first step is to build a system. We will make a UTEM system. We're going to set up a fixed transmitter UTEM system. Select System and System Geometry. There are two options for the antenna layouts, moving and fixed transmitter systems. Choose a fixed transmitter. Then choose an absolute coordinate system in X, Y, and Z for the survey. Next, set the antenna. The antenna were set previously. The list box shows the selections of available antenna. The receiver is set to the Z dipole, the transmitter to the loop. Click OK. Next, select the waveform. There are a number of waveforms available. The UTEM uses step response. However, one can use impulse, frequency domain, and user-defined waveforms. Select reversing periodic waveforms, and we're going to change the frequency to be 30 Hz. Select OK when done. Next, the gates have to be set up. In this example, the gates have already been set. One sets the gates by clicking the UTEM box. We're going to scale the gates to the length of the half cycle. Here, the waveform is divided into 1024 equal intervals. We're going to choose 10 logarithmically spaced gates with a ratio of 2. The gates are shown in the list box on the left. As we scroll through the list box, one can see the interval start times and the end times in terms of the way we divided the waveform up in 1024 gates being displayed. The zero channel is the empty time between the start time and the beginning of the first sample. We could delete that and click OK when done. Next, set up the presentation. Presentation is just a way of normalizing the data. We're going to choose continuous normalization. We're going to normalize by the magnitude of the primary field. We're going to display our results in percent, and we're not going to have any normalization of the waveform. Click OK when done. And this completes the setup of a UTEM fixed loop EM system. In the next section, we calculate the scattering currents and the scattered fields. To calculate the scattering currents, click Calculate and Response. A text box will appear. The text box logs the calculation as it progresses. The first step of the calculation is to calculate the mutual inductances between the cells in the model. This part of the calculation is divided into 5 steps. Here's step 0, and now step 1 is done. We should point out that this model is quite large. It involves well over 1,000 nodes and is modeling 2 closely coupled half-planes. Typical models might include a plate of, say, 400 or so nodes, and if such a model were being calculated, the calculation would have been completed by now. The next step is to solve the resistive limit response. This is the longest part of the calculation, and we have plans in the future to optimize it. You might just want to skip along about a minute or so in the movie while this is being calculated. The movie is still progressing. We're just calculating the resistive limit. Okay, the resistive limit is calculated. We then calculated the inductive limit response, and now we're time-stepping through the solution. The columns show the various attributes of the calculation. The leftmost column shows the step number in the time step. The next 2 columns to the left show the current number of iterations required to get through a step and the total number of iterations required to have made the calculation so far. The rightmost column is also important as it shows the residual error that has to be minimized to complete the time stepping. We can see here the time stepping is quite efficient because the number of iterations in the second column is small. We've now switched solver modes, and we're going to a late time solver. The time stepping will proceed until the residual error or the residual fields in the right hand column are minuscule compared to the initial fields. That is, basically until all the energy of the fields has decayed to zero. Again, we're time stepping slowly now because the model is quite complex. However, if we'd chosen a simpler model, this part of the calculation would also have been done by now. This is one of the advantages of Multiloop 3, is that it can handle a very large and complicated meshes. Okay, the time stepping is done. Let's now calculate the scattered fields. Select Plot and Traverse Line. Then just select OK. And we can see the plotted scattered fields shown in the profiles. We can use the wheel manipulator to rotate the model to look at our results. And this completes the field calculation part of the demonstration. Now we're going to export our data and save our model. We'll select Exports to save our data and then Log Response. This brings a file dialog up. We can type the name of the file that we want to save in the Save As text window. Select Save. Select Save Existing Data to File. Now we're going to exit Multiloop 3. Save the model and then close the window. Then go to the Multiloop 3 menu item and select Quit Multiloop 3. We're now done our modeling session. In this section, the data files are imported into Excel. Here we select Excel. We then select File and Open. We then select the file that we just wrote with Multiloop 3. This is in text file format. Here's the text import wizard. We select Delimited, Next, select Spaces, Next, and select Finish. The data are now in the spreadsheet. We now have to open up a column for our x-axis for plotting. So here we open up a column, and then we copy the x-axis data we want to use into the new column. Next, we select the data we want to plot. We hold down the mouse and just drag it over the data we want to plot. We then select the chart object, select the graph, select Next. We don't have to do anything, we just select Next, and select Next without filling in the various chart items. We then just plot it in the spreadsheet by selecting Finish. And there's our data. This completes the demo of Multiloop 3. Thanks for watching our video. If you have any more questions or comments, please visit geophysics.kos.net. More videos are planned soon.